over the past several years, there's been quite a bit of discussion surrounding advancement of nuclear and the understanding that nuclear is critical to meeting our clean energy needs as a nation and in a global sense as well. The Department of Energy has been heavily involved in those discussions. We've held a variety of workshops. There was one at the White House last year in November. There's one even earlier than that called Nuclear Innovation Workshops, where we had 6 simultaneous workshops across the country. And we were asking these sort of simple, fundamental questions. What does it take to innovate? How can the Department of Energy help industry to innovate? And how can the Department of Energy help your common citizen to innovate? So the Department of Energy recognizes that there's a sense of urgency associated with meeting some of our clean energy goals, and also recognizes that nuclear energy is a critical part of that. So it's time to put our money where our mouth is, so to speak. There is a global demand for nuclear energy that's increasing. There's a national demand for nuclear energy that's increasing. And it's also recognized that our leadership as a nation is eroding in the field of nuclear energy. There are people that are getting ahead of us right now. So if we want to have an impact globally and we want to influence what happens globally, we really, really need to get on the ball and start to develop some of these new technologies in a very, very rapid way. So the GAIN initiative, and I'm just going to start off by saying that the GAIN initiative is an initiative. It is not a program. It does not have its own explicit funding yet.
Can you take questions as you go along?
Sure.
Yeah. Is this coming from the R3 kind of platform? That idea, what you were saying there about being ahead of other countries, the kind of formula that starts after Sputnik, is that what?
I don't know that we need to be ahead of other countries, but we need, the United States, it should be a technical leader globally. So if we want to influence what happens on a global scale, we need to be in a leadership position. So GAIN, the Gateway for Accelerated Innovation in Nuclear, as I said, is an initiative. It's a philosophy. It is intended to guide relevant federal programs. So primarily in the Department of the DOE Office of Nuclear Energy. So the way we do this is underlying all of this, we're trying to meet 3 strategic objectives. These are maintaining global technology leadership, enabling global industrial leadership, and assisting in optimized use of nuclear energy domestically within the clean energy portfolio. And we need to do this hand in hand with utilities and vendors. So it's a public-private partnership in that sense, and the Department of Energy, which is publicly funded, is working with private industry. And we're doing this simultaneously to more rapidly achieve our ultimate objective, which is rapid and cost-effective development of advanced innovative technologies. And just in case you didn't know, that the GAIN initiative was first announced in November of 2015. So again, because of this sense of urgency, historically we've used more of a sequential process to innovation, where a federal entity like the Department of Energy might invest funds in developing innovative technologies, and then a vendor might choose to take some of those innovative technologies to commercialization, and then following that, a even smaller subset of those innovations get deployed commercially. So the premise of this is to integrate all of those at once, work closely in this public-private partnership with industry so that we're solving problems real time, or we're attempting to solve problems real time. That doesn't mean we're just throwing money at it. That means we have to have people that listen, we have to have people that understand the problems that are the most relevant to industry. And we need to guide our federally funded R&D programs with that in mind and with that sort of input. So just sort of a listing of what some of the problems and issues are, what we propose to do. in this national and global discussion, it's recognized that, first of all, the time to market for nuclear technology is far too long. So we need to do something to address that first and foremost. It's also recognized that the facilities needed for studying and developing in the nuclear field are very, very specialized and very, very expensive. Fortunately, a lot of this infrastructure exists within the Department of Energy complex, but it's also recognized that that stuff is not historically easy to access. So there is a concerted effort at this point from within the Department of Energy to open up those facilities to the public. That doesn't mean you can walk into our hot cell and start handling radioactive material. What that means is that you work with someone like myself or Brendan to perform work using federal facilities and utilizing federal expertise. There are tens of billions of dollars that have been invested in these facilities and maintenance of these facilities, particularly over the past few years. And Brendan will get into the Nuclear Energy Infrastructure Database, and you'll get a glimpse of the vast number of facilities and the expertise that exists within the DOE complex that is at the public's disposal. We are taxpayer funded, so it only makes sense for the Department of Energy to be stepping up. So what we need to do is provide innovators in the nuclear field, and we're not talking about, we're talking about the spectrum of companies, you know, from a GE Hitachi all the way down to something like Transatomic, or even a couple of guys in their garage, although it's going to be a little more difficult to vet somebody like that, but we'll do it. Focused research and development opportunities. I'll talk about one of our pilot programs that we ran this first year during the inaugural year of GAIN. And also, it's recognized that the regulatory process can be very, very complex, particularly if you are not accustomed to it and you're a small company without a lot of horsepower. So the Department of Energy will expand on their work with the Nuclear Regulatory Commission to work with these companies to enable, to accelerate their movement through the regulatory process as well. You'll hear about two valleys of death with regard to commercialization of a new technology, and GAIN seeks to encompass and to accelerate movement across both of those valleys of death. The R&D test bed it really covers sort of lower technology readiness levels. This is largely covered by the nuclear science user facilities, which allow access through a competitive process to most of the DOE complex and partner facilities. And these partner facilities include universities. Berkeley is actually a partner facility. Michigan, MIT is a partner facility. The idea is to really bring all of this expertise and capability into a cohesive unit, single point of access, so that it's very easy for somebody. It's not confusing when you come to GAIN and say, hey, I want to do X, Y, or Z. Where do I go? You can ask that question of GAIN and hopefully get an answer. The other part of this for higher technology readiness levels is a demonstration platform. It can be very, very risky and expensive to for example, build the very first reactor of a new kind. So GAIN will, and that's a little more in the future, but GAIN will be working toward a demonstration platform to assist in that part of the technology readiness spectrum. What's happened through the history of development of some of these reactors? At Idaho National Laboratory, as an example, the experimental breeder reactor program. There's a lot of data there that people may not necessarily realize exists or have access to. So one of the focused R&D activities that we've sponsored this year during the inaugural year of GAIN is called the Any Voucher Program. What these vouchers are, as I alluded to earlier, you can't just walk in and throw something in our test reactor at Idaho, for example. These vouchers allow small businesses to lay out some plan, and these are intended to be small in this first year. These will be one-year turnaround projects. A total of $2 million was awarded this year, which is not a lot when you think about nuclear technology. However, we're looking at very isolated small problems. This is a pilot program to see how well this works. The way these vouchers work, you're awarded on a competitive basis. There were 29 proposals this first year. 8 of them were awarded at roughly $250,000 apiece. And what happens is that on behalf of any of these companies, work is performed at the facility that's listed on the right. And you'll see here that we're crossing, we're utilizing several of the national laboratories, as well as one of our partners, the Massachusetts Institute of Technology, and their test reactor there. This is for development of some fuel cladding. The other thing that we've recently been focused on, as I said, it's critical that we have industry alignment. So what we've done is we've gone out and we've looked in technology-specific areas, reached out to the community and said, hey, come tell us what you want. We're going to look for common needs that we can address through, that it's appropriate to address the Department of Energy using taxpayer dollars. Some of the first 3, by the way, were molten salt reactor technologies, fast spectrum reactor technologies, and high temperature gas reactor technologies. And so, you know, we had everybody in the room from GE Hitachi was there, Ariba was there, Transatomic Power was there, TerraPower was there, you know, all of this whole array of these designers. A lot of these, incidentally, if you haven't seen it, there was a Third Way report about a year ago that lists some 50-odd entities that are involved in advanced nuclear. And these are the kind of people we're reaching out to, which leads me to another point, and that is, you know, we're working closely with these think tank organizations like Third Way to help facilitate that interaction between the federal side and the private side. So we were discussing R&D needs, non-specific R&D needs. We're really trying to help as many people as we can, as quickly as we can, as efficiently as we can. So just some examples of what we might be talking about with regard to non-design specific R&D, you know, multi-physics modeling for liquid fueled systems, for instance, chemical thermodynamic databases, reactivity management, so on and so forth. So you get the idea. The GAIN initiative at this point is a very small, agile group. It is built this way by design because in its inaugural year we need to make a lot of progress. Inaugural years, I should say. We're coming up on year 2 now. The director, Kamal Pasamatoglu, will actually be stepping aside for Rita Barnwald, formerly of Westinghouse, here shortly. The deputy director is at Oak Ridge National Laboratory, Doug Crawford, who, by the way, extends his apologies. He couldn't make it today because Delta Airlines wasn't innovative in their power technologies. We have an executive advisory committee consisting of industry, academic, national lab participants. We have an integration working group that integrates the advice given by the advisory committee. I actually sit on that. Hussein Khalil is the chair of that. And then we have a coordinator and a technical interface, which is me. And the rest of this org chart will be filled out soon over the upcoming year. So in summary, we're really hoping to work hand in hand with industry, with vendors, with utilities. You know, we want taxpayer dollars to mean something. We want them to go toward a good cause. We've done some things recently involving the voucher program, technology-specific workshops toward these objectives. For more information, my email is not up there, but you can find me on the GAIN website, Twitter feed, Facebook feed. Emily can give you all kinds of information. And definitely feel free to reach out to me as well. Any questions?
So you said that you reach out to people and ask them why. but you put an important caveat in that it has to be something that's can be, usefully spent taxpayers' money on. So my question is, if one of those 50 startups came to you with something that really you thought you decided that the taxpayer should be spending money on, is there an avenue for them to still access that network?
Well, I should clarify, we're not always using taxpayer dollars. We are using taxpayer-funded facilities, but a company like that can walk in and set up a strategic partnership project, which is fully funded by that company, and still use the facilities. So.
When was the next application?
I'm sorry?
When's the next application?
Oh, for the voucher program? So the next voucher program, if I had to guess, would be in March or sometime around there. We are waiting to see. One of the things we're working through right now are contracting issues. It's recognized that it's very difficult to contract with federal entities. So we're working to facilitate those interactions as well. So we're really looking hard at that right now. Once we get that straightened out, we have lessons learned, we'll release the next one. You should keep in mind, though, if you're not aware, the Consolidated Innovative Nuclear Research Funding Opportunity Announcement is being announced this week by the Department of Energy. If that's your way to access the Nuclear Science User Facility, that's also the way to access Nuclear Energy University Programs funding. And that is a funding opportunity. There's many, many millions of dollars available there.
You may or may not know I spent most of my time before coming to INL at Penn State teaching nuclear energy, doing research there, so I prepared far too many slides, so I will try to move through them relatively quickly. The Nuclear Science User Facilities is not technically part of GAIN. We're aligned with GAIN. We certainly support the GAIN initiative, but we also have some other non-GAIN, maybe more widely spaced access issues. So has anybody here used a user facility, Department of Energy facility in their research? Well, there are about 50 of them, and these are basically large capital investments, billion-dollar, multi-billion-dollar investments, things like advanced photon source, spallation neutron source, synchrotron light sources, that are really too big to build for a private entity, for a university. So they were built to do science, to do, well, mostly science research by the Department of Energy, and they're accessed cost-free by researchers. They write a proposal usually to the specific facility, and they get free access. This doesn't pay for travel, it doesn't pay for your time, graduate student stipend, anything like that. It's really just access. Now, these are all mostly owned by the Office of Science, and they basically do basic science research. So up until 2007, there really wasn't anything to do nuclear energy research. And I was going to show you some org charts for the Office of Nuclear Energy, the Department of Energy, because a lot of people don't really see how that fits in. But basically, Office of Nuclear Energy is really less science-based and more engineering or applied engineering. We're looking at doing things like supporting the current set of reactors, deploying advanced reactors, creating a sustainable fuel cycle, supporting non-proliferation efforts of other parts of the government, Department of Energy. So in 2007, the Office of Nuclear Energy inside the Department of Energy decided that they had some facilities that would be like this, and they'd set up their own user facility specifically to support nuclear energy research. So they set up the Advanced Test Reactor National Scientific User Facility, which is now the NSUF. But basically what we look at studying is, like I said, these DOE NE missions, maintaining the current fleet of reactors, so things like life extension, aging issues, cracking in materials, better fuel performance, things like that. But then also advanced reactors. And as you may or may not have covered these 2 weeks, there are very few new ideas in nuclear. So when we talk about advanced reactors that are molten salt or metal-cooled or gas-cooled reactors, much of these technologies at least have their roots 50, 60 years ago, sometimes older than that. But now we have advanced materials, we have modeling and simulation capability, lots of new testing and characterization equipment. So things that were really not pursued earlier can be pursued now. So specifically, NSUF looks right now, our current mandate is looking at irradiation effects on fuels and materials. So most of our capabilities will reflect that. Office of Nuclear Energy, not necessarily unique in DOE, but is very user-focused. So if the user community says, gosh, we're really short on thermal hydraulics test loops for molten salt reactors, then that's something that would come to me, and we'd look at, can we build or partner and make some more of these available. So one of the things that I will mention early on, Office of Nuclear Energy, the R&D programs, the managers in there, if you now or in your future career have some input, you need to contact them. There is no way they're going to get information about what the community wants if there's not interaction. And at some point you may bother them enough, they tell you to stop calling them, but they probably won't. But like I said, the real thing is they don't have their own agenda. They want to support the missions of the Office of Nuclear Energy, which I mentioned. So the initial things that were available in the ATR NSUF at the time were the Advanced Test Reactor. You see a core schematic there. A very unusual reactor. If you're familiar all with a lot of the test reactors, they're usually a very small core, very high flux environment. The ATR has 77 positions inside. It was originally built in concert with the Navy to do fuel development for its programs. But lots of positions, and the ATR became part of this user facility because at the time, it really wasn't being used that much. There was a lot of empty space in ATR. That is no longer the case. ATR is almost fully subscribed right now, so this year we have had to fight a little bit to get some spots for our researchers in ATR. And the companion facility to ATR was the hot fuel examination facility. And this really doesn't do a good job of showing you how big this is. You can sort of see the windows over on the sides. Those windows are about 4 feet tall. So this is this part of the cell is argon filled, made originally for the fuels examination from the ATR and the treat reactor. There hasn't been anybody inside this cell in probably 40 years for a couple of reasons. It's the argon atmosphere inside that is also highly alpha contaminated. We'll talk about why that's a challenge for us in the future. But there's 25 windows, so there's essentially 25 sets of manipulators. Huge amount of work you can do in this cell. So this was the ATR NSUF for a while. Now, then we came up with some different ideas. So this was great, this got use, but then the Office of Nuclear Energy said, well, what else is out there? So over the last 8 years, NSUF has really become a consortium, or sometimes you hear it say a lab without walls. So we have INL and the facility is sort of at the center, but there's facilities at Oak Ridge, at the different universities. We have facilities at Pacific Northwest National Laboratory. We just brought on the IVEM, the TEM microscope with ion beams. Brookhaven, we're bringing on the National Synchrotron Light Source 2. We'll have an irradiated materials beamline, and we'll talk about some of the other capabilities. But this is what we've got right now. Certainly, Professor Hoseman's materials laboratory here at Berkeley is an integral part. We've supported quite strongly. And we're always looking at new partners. This will probably almost double in size in the next couple of years. And all these facilities are available for access through our process. Go ahead.
Before I create Texas A&M complaining that they're not part of this, to be part of this, is there plans for them to join?
Texas A&M is certainly on, yes. Now,
Can I still do this week?
partnership in the NSUF is completely and totally voluntary. They don't have to do any work they don't want to. They set their own rates, that sort of thing. So Texas A&M will be invited, particularly Professor Shao's ion beam laboratory. Yes?
I understand, for example, the IBM is already open to accept people's proposals. How does this change its original plan?
It's a very good question. I mentioned very early on about most of the user facilities in the US were Office of Science. So they were, if you came in and said, I have a proposal, I'd like to go to IBM, and it is to examine irradiated reactor vessel steels to look at, I'm not a material scientist, so I'll say something wrong, to look at something. They very well may look at that and say, well, that doesn't support the missions of the Office of Science, so no. There were some funding issues with IBM through the Office of Science, so Office of Nuclear Energy has taken over funding for that. And the original process still exists. And IBM can do whatever science-based work it would like, but Office of Science has to pay for that. Office of Nuclear Energy said we will pay for up to 100% of IBM's time for nuclear energy associated research. So if they fill all their time with any research, then we pay for that. Well, Office of Nuclear Energy pays for that. If not, Office of Science pays for it. So you can still apply the old way, but if you can also apply through the NSUF to get access. The costs are the same to you, zero, so it's a little different. Please, go ahead.
Just curious, what is Purdue just?
So Purdue is, I've got a quick slide on that, and we'll certainly should show more, but it's, they have a number of ion beam facilities that are low in the keV range. So it's very high flux, high intensity surface science. So there's a lot of neat work that goes on there. They haven't actually done a whole lot of NSUF work, but they do an awful lot of work, and it certainly is available. Also, the same thing, I'm the infrastructure guy for Office of Nuclear Energy, at least for NE4. So if there's something at one of the universities or something that you see that you think would be useful for lots of people, what we're trying to really do with this is unique, hard to access facilities or oversubscribed facilities that have sort of a generic, widespread use. If it's only one single program, maybe we'd add it, but if it's something that's very broad-based, it's really interesting to us. So I'll spend a couple of minutes talking about how you access the NSUF before I talk about what it is more than this. Like I said, we're really radiation effects, fuels, and materials, but there is interest in thermal hydraulics. We're adding modeling and simulation capabilities in, and we, once again, respond to the community. If there's something that's very important, certainly gain talking to the industry, that's something we're interested in doing. So as John mentioned briefly, the CINR is the general R&D call for external entities to access DOE funds to do research. That is being kicked off this week. The funding opportunity announcement, basically the document for that, will be released Friday. There are draft work scopes, or essentially areas in which you would apply to do work, out right now. The webinar is going on right now while we're here. They will all be available. The webinars are recorded. They'll be online at nup.gov and also at the Office of Nuclear Energy's website. But these are large calls. They happen once a year. They're R&D funds. So you basically go 3 different ways. You can get just R&D funds if you don't need access to any of our facilities. You can get R&D funds and access, or if you somehow have funding elsewhere. You have a program that's already going on. You just realize now, hey, it would be great to have access to, like I said, these ion beam facilities or something like that. You can apply for what we call access only, which is just the access, no travel, no R&D funds, something like that. These are big, and a radiation experiment can be $5 million. We're thinking, well, we don't know since there's not a budget right now. 2 years ago, I think we awarded about $6 million in projects. Last year, we awarded about $10 million. We'd like to award about $10 million again, but that depends on the federal budget. The House budget would put us there. The Senate budget puts us pretty far away from that. So we'll see what actually happens. The applications for this will be due, they do pre-applications and full applications in a sort of a filtering process. The pre-applications, I think, will be due sometime in November, December. Full applications will be due about February. A lot of different things you can do with that. Because we realize that that's not what everybody needs, we also run 3 calls a year for rapid turnaround experiments. These are smaller, usually say about 6 months to get them done. You can access any of these facilities, really except for test reactor radiations. They take years, so they wouldn't fit under this. But you can do ion beams, you can do research reactor radiation, you can just do post-irradiation examination, materials characterizations. Those we fund. Some calls we funded 75% of the. This year we've funded probably about 50%. And then, as John also mentioned very briefly at the end, the first 2 steps up here are all open data. So you publish your research, it's taxpayer funded, and nothing can be proprietary. You can also do cooperative agreements or work for others, which is basically fully proprietary work, but then you pay all of the cost, and that can get quite expensive, but it still does at least get you access to these facilities. Over the last few years, we've done hundreds of projects. We'll probably double this number between fiscal year 16 and 17, because since our budget went up, we were able to do a lot more work. There, I mentioned ATR doesn't have a lot of excess capability, but some of these other facilities do. And if we don't have that in ourselves, we'll partner with somebody else to do it. We do have a pretty high acceptance rate on most of our applications. So it's not like some facilities. I think IBM was 300% oversubscribed at one point. So they would have liked to accept three times the number of proposals they were able to. So since I am the infrastructure person, I'll talk a little bit about this new initiative that we started a couple of years ago. Go ahead.
Just a quick question for you, Mr. Section. How do you, kind of for both of you, how do you currently find out what your, the people that you're asking, what they need, what they would like to do? How do you currently find that out?
I'm going to get to that. So at least talk about that from the point of view of infrastructure. So a couple of years ago, the Department of Energy realized they didn't have a really good idea about what they had. They knew they had somewhere on the order of $100 billion worth of infrastructure, so they obviously knew where things were, but on a smaller scale, they didn't really understand the capabilities. A lot of the different R&D programs have their own set of equipment, they do their own set of work, and not really deal with those. So, like I said, 2 years ago, we set up this infrastructure management program. So the first thing we did was came in here and built a database, and this is this nuclear energy infrastructure database. I'll give you the address for that. That has a very large proportion, well, not quite say all, of the nuclear energy associated R&D infrastructure in the US, and we're starting to build that in the rest of the world right now. And then we do look at this R&D direction, and we have a bunch of different ways of getting to that. Certainly, like I said, the CINR, people apply to do research in certain areas. I look at all those applications, and from that infer both the area of research they're looking at and the infrastructure they would need to use that, to do that research. From that, I produce a gap analysis once a year that says, here's what people are looking for, here's what we have, here's what we need. And from that, we may buy new things. And obviously, nuclear energy doesn't have a pile of money, but they do have money set aside to build new capabilities. But then also, we may just partner with other places. So if, like IBM, that was an area we needed, there was some synergy there, so Office of Nuclear Energy took over funding that. And then this is a cycle. We add new things to the database, and we do this every year. When we looked 2 years ago, we found out that the big needs were test reactor radiations, ion beam facilities, and materials characterization. So that was the areas that we decided to focus in to spend our money. We've got almost 900 instruments, and these are basically capital instruments, so things that are $500,000 or more that basically you can't just go out and buy on a research grant. And we have over 100 users now. We have lots of data in the database for each of these capabilities, so things about where they are, what their capabilities are, what detectors they might have attached to them, common things, and then specific ones for different types of instruments. This database is accessible to everyone. I have some pictures of the old database. There's a new one rolling out this Friday, but it'll be the same functionality, just a different skin on it. You just have to register, we give some information, we just verify you are who you say you are, give you access, you can go in and you can see all these things. You can, like I said, you can browse for the data, you can search specifically for interesting things. We have some GIS data on there. Institutions, there's not very much data on that, it's just where it is and who owns it, and then what facilities are associated with it. You can go straight to facilities from here. Facilities have a lot more data, then they also list the instruments that are associated with them, and then the instruments have the sort of final set of data. And we try to have lots of links to user manuals, points of contact, users' organizations if they exist for this, so you can go in and learn more. Like I said, we can do plain text searching, so that's helpful. Reactors kind of a silly thing to search for. There's 80 reactors in the database. But if you were going to search, you need to work with curium. Well, minor actinides, there are very few facilities that can work with that. This will at least narrow it down pretty quickly to what's available. The new formats is a little bit cleaner. We also link not only to the instruments, but to materials. So one of the things I mentioned is you can do experiments that don't require irradiations if you already have irradiated material. Now, not lots of people have that, but we do. just as the Department of Energy sort of accumulated lots of capabilities over the years, we've also accumulated lots of materials. So these materials, it can be legacy materials from either old experiments or old reactors. So John mentioned the EBR 1 and 2. We have materials from those. We have materials from other decommissioned reactors and old experiments. The only really vital thing with any of these materials is that they have a full history and provenance, so that you've got the heat, the chemical data that went into it, the temperature, the fluence, the spectrum. Otherwise, they're not terribly useful. So we have this right now. We've got, this says 3,500 specimens. We're looking at doubling that with some stuff coming up from Oak Ridge. These are just some places where these samples have come from, mostly neutron irradiated. John actually was instrumental in getting us some material through EPRI from Jose Cabrera, Zuzarita Nuclear Power Station. We're trying to get some material from Zion 1 and 2 that have been decommissioned through the Light Water Reactor Sustainability Program. This is just a quick list of the actual material types that are in the database right now. So if you said, okay, I'm interested in looking at ODS steel or ODS, you can say, oh, we've got some. Okay, let me look and see what's in there, what's been done already, and you can just ask for that material through one of the processes. We also run specific irradiation programs that are just NSUF to put more material in the library. So we'll look at some of these other areas where we can get feedback from users and say, okay, we think that's going to be a big area in the future. We'll run an experiment that's just that material, just to populate the sample library. We built some additional improvements. One thing to spend a little bit of time on very quickly, I mentioned we have facility instrument database, we have a fuels and materials database right now, but we have other things. So we have all the research that was done. We have expertise, so that's one of the things that GAIN is offering that NSUF really never did before, is actual access to people with expertise. What we didn't really have in this is the data. So there's an initiative right now to try to get this data that's been developed over really the last 70 years or so by the Department of Energy and the Atomic Energy Commission before that. All this test data, it exists, but it's in file cabinets, in paper reports, maybe in scanned PDFs. So there's an initiative right now to get that data in a form that's useful. I mentioned old, there's very little brand new technology. So if you're looking at molten salt reactors, it would be a really good idea for you to have access to all of the stuff that was done before and not to sort of start that process again. So as part of all of this, we're looking at taking our instrumentation database, our materials database, our research projects database, and our expertise, and putting it all together into one sort of storefront. So a new researcher or an existing researcher can come in, say, okay, I'm interested in going down this path. Okay, I can see where the work was done, and look at the data. I can see what materials are available and all the history on that. And this helps both sides, because this helps us look at it and say, okay, here's a proposal, looks good, let me go see if it's been done before. And it helps you write a good proposal, because you can look at it and say, okay, this has been done before, but they didn't do this right. Or this area over here is missing, so I'll write to that. But this will provide a much easier way for everybody to work. I think I'm probably talked out my time. So these slides are up there. You can go ahead and look through the rest of them. We're talking about, these show us some of the things that we're looking at being able to do with this data in the future. And then a quick set of the, going through the summary of the capabilities that are available. All of this is up on the NSUF website. This is the website, or the particular link to the infrastructure database, but you can get to it from the NSUF website or from GAIN's website. And that's my contact information. So I can take maybe one question, and then we'll go to Ron. Go for it.
How do you deal with data that's not written down? So again, in the UK, lots of the people who are about to retire, or they've got a lot of knowledge that isn't written down. Is there any initiative to try and get some of that information?
So there is another program, and I don't know if you would hear about it or not, called the Nuclear Energy Knowledge and Validation Center. And that's to do all data, but specifically they're looking at legacy data right now. And they don't have a very big budget this year, but they are looking to grow because there's a huge amount of that.
So there's a user community around that? Does that help?
I would expect so, yes. NSUF is actually working with the UK user facility and the National Nuclear Lab on some other partnerships, and the Fuels and Materials Library we're looking to partner. That's actually going on right now. So we can share materials and other capabilities across. One thing I didn't mention is that international researchers can access NSUF capabilities, just like US researchers. We appreciate if there is a US point of contact. It just sort of makes it easier, but that's not forbidden anymore.
Basically, I'm a materials engineer, and what I want to talk a little bit about here, we have lots of facilities, and you have materials in the past, lots of experiments, but in reality, I represent GE, a supplier of nuclear systems, and what I want to talk a little bit about is another critical part is I'm going to have to make something. Not, the experiments are very interesting, but I want to make hardware. I want to make it very efficiently or effectively, and I have to be very prudent. I mean, this is an industry that we can't really have we really can't tolerate any failures. We want to have high integrity materials. So, in reality, as we go forward, we have conventional ways of making materials. They have certain restrictions. They're oftentimes very costly. I have proven databases that I use. The ASME code is very critical. And in my interactions with John, we realized that particularly GE is very interested in additive manufacturing. And if you look at something like GE Aviation and probably GE Power, they will be using additively manufactured materials in planes or for components, for instrumentation, for valve bodies and things like that. And what we, in our interaction, we said, well, why we would like to use these kinds of materials both in current operating plants, if we have replacement parts, and also as we go forward into future plants, particularly maybe small modular reactors. There may be certain configurations or materials I want to make. They may be special in composition, other things. So I would like to have the ability to use these advanced manufacturing technologies. And I'm going to talk a little bit about just why you might use 3D, what we've done. This is really 3D printing, but we call it additive manufacturing. John talked about, and Brandon maybe, using the facility where an organization like the Electric Power Research Institute was interested in a product form that was already perhaps in the code, but there were certain properties were needed. They're running programs with ATR and the test facilities INL to confirm that those materials have certain characteristics as they get irradiated. So basically my talk is just about this one aspect of how we might use 3D printing. So I'm just going to give you, are you all familiar with 3D? You all probably have 3D printers in your house, possibly. I don't know. I don't have one. But this is really directed at metals, and just give you a little bit of a background on that. And when I look at it, I try to say, why do we want to use this? One is proving a concept to product very rapidly, and rapid prototyping. And there might be times when you want to just rapid prototype things in plastic, show it to a customer, look at how it might fit together with something else. You could use it as a way to evaluate new designs, and you could try things in a test facility or in a mock-up situation and see how it works. And then the other thing would be just rapid building of hardware. There may be times, particularly where if you use castings or other types of metal products, it takes a long time to get it, but if I could make it by 3D, I could have something very quickly. Now, it's not necessarily always the most inexpensive, because I generally go from a powder, as you'll see, to a product and maybe some post-treatments to make sure it has integrity. So I'm going to talk a little bit about that, and then I'm going to talk about the role of gain. And when I came here and worked with John, I'm looking at myself as having two hats. I definitely work for General Electric, and we want to both sell products, we want to support customers that already have our products, but I'm also a US citizen. So I'm looking at this program as a way to help generically get this type of manufacturing in play, and not sort of what I say, be scared of the dark. Because one of the big issues, as they talk about here, when I irradiate materials, I can't, one, it takes a lot of time and effort to get there, years, Then I want to do characterization. I want to, say, hey, this is okay. Now I have the database. Now I can go to my customer. Now I can go to the regulator. Now I'm okay to use it. I'm hoping that this program sort of sets up sort of a generic strategy where you build some things, you show their correspondence to raw products, you look at irradiated properties. In this case, maybe I'll talk a little bit about our GAIN program or our NS. I'm getting confused. These guys represent different people, but it's an NSUF program. And then use that to say, the next time I want to use additive, if I can show certain things in unirradiated characteristics, I'm not worried about using it in certain applications. So I do have a video, and afterwards, if someone wants to see it, it's not really super exciting, but it sort of gives you an idea of how you might do 3D printing. One, you can see up here that I've got a computer. The real nice thing is I can have a designer. A designer can make a CAD model. It can immediately go and be used to control a laser beam, and then that laser beam can be used to basically fabricate the part. In this case, this is called direct metal laser melting. Sometimes it's called laser sintering. I think they're very similar. And basically, you have sort of a table here that is covered with a powder. So you have to start with powder. And then you can see that brown piece, that would be the part you're building. And then I put a layer of powder, I sinter it, only the areas that I'm interested in building the product. Then I move the table down, put another row of powder, and do the same process. If I want to make it have the properties of materials, I do need to do some post-processing. What we call hot isostatic pressing, heat treatments, other things. I may have to do slight machining, but I'd really like to minimize the machining. I'd like to go direct product to use if I can. And these are just some products that other GE businesses have used. I think that the top piece is something made for power. This little piece here on the left side is something that may be like a sensor fitting, something that's probably maybe potentially flying in a new GE engine now or in a very short time. I just took some screenshots from this video, and you can sort of see here is sort of the upper part, the bed, and if you look at the green surface, that's really all powder, and you can see the product that's being developed. And now you see over here, you can see the white beam, that's a laser beam making the fusion. And you can sort of see that I'm building up another product on that part. If you, at the end of the process, so you've built multiple layers, you actually do have a reservoir of powder that's left over surrounding the fused part. So that's what the upper left-hand corner represents. The middle one shows the products, and then the bottom one shows maybe the final pieces that I take out. What I see is there's an efficiency. If I could use that whole bed surface, let's say I'm going to make a whole bunch of parts, and I use the whole thing, then I'm not going to have so much residual powder. So there are some areas where it really makes sense. And as you can see, particularly these parts here, I don't know if I have a good picture of those, they're fairly complex structures. They could be some kind of, and I'll show you one application that we have, where I have sort of a 3D structure that may, in the case for us, prevent debris going into the fuel. So there are certain aspects that it really lends itself, particularly complicated structures, that you really would have to look at how do I put this together rather than I build it directly. So basically, these are sort of my words. I've got a great idea. And that's what you guys are here for, right? You all have great ideas, maybe all analysts. I don't know if you're mechanical engineers or whatever. Okay, I want to implement this, and I want to make it. So, and I'm designing something for unique performance. And I think as some of the things that Brendan talked about, some of the new reactor concepts, there may be little components that are really critical to getting the performance you need to make it effective. And so I want to get away from the constraints of, I can't make that, or I've got to machine it, it's very costly. So I've never done it before. One thing, I only need one of them. Let's go off and build it, see how it looks. It'll take too long. In this case, I can at least make some prototypes. I may not do all the heat treatments, but I can see how it works. I may use it in some test facility. So this is really where we see additive manufacturing. An example would be aircraft engine. Aviation, GE Aviation, a lot of the turbine blades, you know, they require cooling, so cooling passages. Maybe there's you know, one of you guys does a, you know, some type of program, you know, thermal evaluation, and you say, if I have these channels this way, it's very effective. I can get another 20 degrees of operating temperature or something like that out of the material. So first I'm going to talk about 3D prototyping. One, you can rapidly visualize things. And for us as a business, we use it with customers and say, look, this is what we're going to build for you. We do some repairs. I work mainly on operating plants, you all in the future, but operating plants still represent 20% of our capabilities in the country. We want them to operate. We want them to operate for 60 years. And clearly some of the initiatives that the national labs have is to move them forward into 80 years operation. So this is clearly something where we may have something that's broken or not easily replaced. We will repair it. In conjunction with some analysis, we can say, I can do these things. So it also can show how I can build things in assemble parts. I can show designs to people in the company. I can show it to regulators. I can do other things with it, show the key features, and I can also do rapid iteration. You know, if I see certain things don't work, or I do a stress analysis and certain areas may be not meeting code or something else, I can do that. And again, develop concepts for installation tooling. How do I put something in? We do a lot of things where we put them in remotely, you know, underwater, under 50 feet of water. We have to have tooling to be able to install them. So this is another area where we're using them. The tooling engineers, we have a BWR training facility, and by the way, if anyone's ever interested in coming to San Jose and going to our training facility, which is a mock-up of a boiling water reactor, feel free to contact me and I'll make sure you can come down and see it. You all may not be from California, so I don't know if that's so easy, but a lot of it is how do you put in certain parts or how do you change those and things like that. So tooling is very critical. The one area where I see this might be very important to us is that, you know, as all the main suppliers of currently operating plants and future plants, we're going to have fuel. We have to make fuel. And this just shows you a fuel bundle, a GE fuel bundle. It's got a lot of rods. You know, they're very thin walled. We've got flow past it to basically, you know, for heating aspects. But what I'm really worried about is if I get some debris, if something comes through there, gets caught, vibrates, then maybe I can get a hole in a tube, and the plant will have to shut down, either change that bundle, isolate it, change the core configuration, whatever. So preventing failures of debris is very, very critical. And the industry as a whole has really changed. There are very few you know, fuel failures in time, but every one represents downtime, you know, and one thing I think we're all aware of that are in the nuclear business, in the US, it's a very competitive market. So if I have fracking and I have natural gas, then suddenly nuclear, which was very cost-effective 5 years ago, now looks less cost-effective. So time and operational costs are very critical. So if I look here, this little portion here, this is just an example of a debris filter. If I could build something up, another layer, have other types of geometry, and I might take this and put it into some kind of a facility to look at pressure drop, make sure that it works, that I have the right kind of characteristics. This looks like, to me, something that lends itself very easily in the long term to additive manufacturing. So that sounds like a great idea. I can build it, I can do some testing, I can iterate on the hardware, I could then actually build it for in-plant trial. Why do I need to work with the government? The one issue is if I have additive process and I have no experience with what happens to that under irradiation, there may be a customer that says, that's a great idea, but I really don't want to put it in my plant. And or the NRC says, we really like that material, but we really would like to see the irradiated data. So interactions with myself and John and some others at GE, we realized there was an opportunity. If we could get experience with additive manufacturing, get it into the ATR, get it into some test facilities there, do some critical tests, just simple mechanical tests, tensile tests, but also do some fracture tests. What kind of fracture resistance does it have after it's been irradiated? This would be very important to assessing or using additive manufactured materials in plant. So again, when I looked at John's slides, I stole this from John, said provide focused research opportunities and dedicated industry engagement to realize the full potential of nuclear. So again, I look at it, I want to improve my products, I'd like to move this technology into products, and I may very well want to use this in future reactors, small modular, whatever. And again, public-private partnership, I think it's really important. We have a mission. You know, oftentimes these research facilities, they're very important for basic research, but you are eventually going to build things, and you're eventually going to have codes that work for that. So that's really important. And I think dedicated to accelerate commercial readiness. So by doing a program like this and having you know, INL and the user facility both do the design of the test so that we know what the radiation levels are, then take it and do the actual examination, the testing, and then more importantly do high resolution characterization. We can compare to unirradiated material. If we see sort of a, you know, a nice path, and we can say, yes, it operates just like raw materials, just like the materials I put in reactors 50 years ago, and I wasn't scared of the dark, so to speak. I wasn't worried. I was going to put it in there, and if it got irradiated and it broke, well, I'll learn about it. What I want to see from a, you know, sort of a national perspective is developing this as a way to generically be able to move this kind of technology into use. So, again, we want to use this innovative manufacturing. GE is a real leader in this, particularly in aviation. We want to assure the customers, the regulators, everything's all right. We're going to do this characterization program, hopefully. The government, hopefully, we're putting in the materials. The government's putting in the money to do the testing and evaluation. And so I think this is going to help both us, and it's going to also help, you know, it's going to help the industry as a whole. Now, the one thing that really comes out of this is the data that we'll generate, or they will generate, and the data that we're going to generate in support of it will be open. Now, the processes we use and some of the process specs will be ours. But there will be this correspondence that if I have these kind of materials with these characteristics, and I've got irradiated data, and we can see this, very much more likely to get the customers and other people to use these innovation, or this innovative technology in real reactors. So that's what I see as the real benefit of having this interaction, and it's really at the supplier level, people building it. We do actually not live in a virtual world. I know Berkeley's soda hall's right over there, and those guys do virtual all the time, but there is actually hardware that's involved. So with that, I think did I have a summary? Just additive manufacturing speeds up innovation, design-driven versus material or process-constrained, specialized materials, you can change composition. We're interested in low cobalt materials. It may be easier to put in powders of low cobalt, then we don't have to worry about worker dose. And so the characterization, we need costly facilities, and that's what the government can provide to us. Okay, that's it. Do you have any questions? Yeah, sure.
So I don't know much about materials, but are the defects decreased with 3D printing?
Do what?
Are defects decreased with 3D printing?
Defects.
Like
Defects.
Yeah.
Yeah, so that, you know, that's critical, yes. I hope those guys in aviation are really worried about those things too. But yes, that's one thing that a vendor would have to worry about is how do I control the processing. One thing about additive that I like, we're all in a digital world, right? So if I'm doing things with lasers, I can get feedback. I can know exactly how I build it. You know, if I have a big hunk of metal and it goes through all this processing, I don't know. One of the programs that I'm aware of that John's worked on is powder metallurgy, which is much further along. It's a way to make castings like valve bodies. And the reason for it is very few defects. And so they're doing sort of a similar program to establish everything's okay after radiation.